Hello, shall we start?
Okay. So I welcome you, everyone to this IEEE webinar, which is organized by IEEE Signal Processing Society student branch of IIT Kharagpur. So let me introduce you to the speaker. Today's speaker is Dr. Ami Wiesel. Uh, he has a lot of achievements, but for the sake of time, I'll give a brief introduction of him. About him. Dr. Ami Wiesel is currently an associate professor in Rachel and Selim Benin School of Computer Science and Engineering, Hebrew University, Jerusalem, Israel. He received his BSc degree in 2000 and MSc degree in 2002 from Electrical Engineering Department of Tel Aviv University, Israel. In 2007, he received his PhD degree in Electrical Engineering from Technion Israel Institute of Technology, Haifa, Israel. From 2007 to 2009, he was a postdoctoral fellow with the Department of Electrical Engineering and Computer Science, University of Michigan, Ann Arbor, USA. Dr. Wiesel is also a visiting researcher in Google since 2018, and today he will be speaking on the title 3 Examples of Easy Non-Convex Optimizations. So before starting the presentation, I would like to mention that the questions and answers will be taken after the session completes, after the presentation is over. So kindly leave your questions in the chat section below. Now I request Dr. Wiesel to kindly start his talk. Sir?
Actually, I always wanted to visit India, but like everyone with the COVID situation, I guess it's going to take a while till we start traveling again. But I hope you will like the talk, and one day we will come visit each other and meet each other in person. So this is a talk, it's about stuff that we already finished like a year ago. So it's been a while since I gave this talk. And it's basically, I'm just going to go and show you 3 examples of optimization problems, which we once thought were very hard and are now easy, the way we see it. And I think this is the main theme of most of what my group does these days, is the whole world is trying to solve deep learning and stuff like that, and it all boils down to optimizations. And I think what we want to understand is, when are optimizations easy, when are they hard, why do we succeed to solve some of them, why do we fail in others? And I don't have an answer for that, unfortunately, but I can give you 3 examples of works that we did in different topics that will maybe give you hints and maybe will motivate you to find better answers. So let me begin. Okay, so first I need, of course, I didn't do this work alone. I did it with a lot of awesome people. So I just want to mention there. So Gal and Amir, I work with them in Google and also in Hebrew University in Tel Aviv. And then there are all the students. I work with amazing students who do all the hard stuff. Yoav, Nafar, Gad, and San. You'll see a few works, and each of them was done by 1 or 2 of these students. And Uri Okan is another collaborator from outside the university. And of course, special thanks to Google Research Tel Aviv. I did my sabbatical there 3 years ago, and some of the, at least the first work, is very much related. Okay, so now let's start. So I think, as I said, the main thing that interests me these days is, when can we solve optimization problems?
So sorry
Now
to
I
interrupt
teach.
you. So can you make
Yeah.
it full screen?
It's not full screen now?
No, not yet, sir.
No, wait. Now it's better?
Yes, sir. Yeah.
Okay, perfect. So I teach, and I guess all of you, 2 courses in convex optimization. Convex optimization is something we understand very well. But today, in convex optimization, did a revolution in signal processing, in communication, and all over, I think like 10, 20 years ago. What we did is we took every problem of optimization that we had and tried to find the closest convex optimization. Unfortunately, the real world is usually non-convex. And before, what we did was try to find the best convex approximation. Today, people just try to solve non-convex optimizations as they are, without any sort of convexification. And I drew here 2 graphs of functions. Both of them are non-convex, but I think all of you, I can't see you right now, but if I would ask you to raise up your hand, if you think that the left one is hard, then everybody will say that the left graph is hard to minimize, right? So lots of bad local minima, which you can get stuck in if you do gradient descent. Whereas the graph on the right seems very easy, right? It has 2 global minima, and it doesn't matter where you start, you end up in one of them. So both problems are non-convex, but one of them is easy and one of them is hard. And I think what we want to do today is understand which problems are easy, what makes them easy, how do we take hard problems and make them easy. These are the kind of questions that we are interested in. So that's the main theme. Another thing I'm going to talk about is, I don't know your background. I think it's SPS. So I guess everybody here is from signal processing and communication. But today machine learning is taking over everything, right? I don't think there's any field in engineering and computer science where machine learning is not taking over all the algorithms. And what I want to show you here, I'm going to talk about problems in signal processing that also have some, an alternate problem in machine learning, and you'll see that the problems are very similar. So I'm going to talk about 3 problems, and each of them will have an application in signal processing and one in machine learning, and I want to convince you that the problems and the solutions are very similar. So one example is beamforming and PCA. PCA is principal component analysis. So you can see here on the bottom the photos. So on the left, you see a beamforming on these antennas from a paper by Nikos Sideropoulos. On the right, you see some kind of autoencoder dimensionality reduction. This is where people do PCA. I guess all the younger people here in the audience will know what autoencoder and PCA are. All the people in my age will be more related to beamforming. But at the end of the day, these are very, very similar problems. Another example is the end of the talk is MIMO detection, which is something that was very common in signal processing communication. On the other hand, today people talk about quantized networks, again, having nothing to do with communication, but the mathematics are exactly the same, and we'll see it later. So I think that's it for the introduction. And now, as promised, I'm just going to give you 3 examples of 3 completely different problems. And each of them will have an optimization that is generally hard, but I'll try to convince you that in some settings it is easy. So we'll start with the first one on robust covariance estimation. Okay, so robust statistics and robust signal processing is a field that I've been working on for almost 20 years now. I'm sure many of you heard about it. The main idea is you're trying to, let's say, talk about robust statistics 101. The first slide is usually you have all these points here. Do you see my cursor?
Yes, it's visible, sir.
Can you see it? Yeah. So we have all those points, and we want to pass a line through. But if we have an outlier here, then we know that when we fit the line is going to get attracted to the outlier. The standard way to fit a line is using something called least squares, which I'm sure you all know. Just take the points and you try to find a W that will minimize the squared error. This is the squared error, the square loss function. This one, it's a parabola, a square loss. We know that this square loss is very sensitive to outliers. So if we minimize this function, the line will be attracted to the outlier and we'll get the wrong line, even though everyone here can see in their eyes that this point here is an outlier, which should be disregarded. The idea of robust statistics is we take this function and we say, well, there's no point, once a sample has a huge error, it doesn't matter if it's this error or more. It's an error anyway, it's an outlier. An outlier, it doesn't matter if it's a plus million or plus 10 million. And there's no point in squaring the error. That's why Haber suggested to take an absolute value here. You see, so it starts quadratic and then becomes like an absolute value. It becomes linear. And this allows us to get rid of the outlier. We just do it by replacing the square here by a function rho here, which starts quadratically and then becomes linear. Now, my graph is like a caricature, and it looks non-convex. It is non-convex, but Huber's function, they set up the slopes exactly, so this function is convex, and people did it like 30 years ago, even 40 now, and it's a well-known method to get rid of outliers by convex optimization. So this is very, very old, and the whole point is replacing the square function by a rho function. In signal processing, we often don't deal with line fitting, but with more complicated problems. More generally, in line fitting, we're trying to find the mean, to fit the mean, the expectation. In signal processing, in many of the works, what we care is about the relations between things, and we want to do covariance estimation. So this is covariance estimation, what's written here. And in the Gaussian case, it's this optimization here. We're trying to find a matrix sigma, which is positive definite. That's the covariance given data point xi. And this is maximum likelihood in the Gaussian case. And if you solve it, everyone knows there's a very simple solution called the sample covariance. You take each of the vectors xi, you multiply them by the transpose, you get the rank 1 matrix, and you average over them. This is the sample covariance, and it gives you a very, very good estimator of the covariance. And people use it all over, in beamforming, principal component analysis, and many other applications. The problem is that just as before, if we have an outlier, suppose one of these xi's is an outlier, which is multiplied by 1,000,000, then it's going to dominate. So we have n equals 100, but we have 1x, which is multiplied by 1,000,000, it's going to dominate the whole sum. And that's why the sample covariance is very sensitive to outliers. This has been known for many years, and people said, okay, let's do the same trick as before. Here we have a quadratic function, you see the x times x. Let's replace the quadratic function by some rho, and put some rho here, and then solve the maximum likelihood. That's called robust covariance estimation, and there are lots and lots of papers on it, both in statistics and in signal processing. When you try to minimize this, you don't have a closed form anymore. What you get is, you get this equation here, where you see the covariance depends. It's just like the sample covariance before, but there are these weights here. And the weights depend on xi and sigma. These things these values here are weights to try to estimate whether each of the xi's is an outlier. You can think of it as this thing being usually equal to 1, and then you get the sample covariance. And once in a while, if you see an outlier, you put a 0 here, and then you ignore that outlier. The problem is that this is not a solution, because you've got sigma both on the left and in the right. So you need to iterate on this thing and do a fixed point iteration and hope that it converges somewhere. You do like 10 iterations of this and hope that it converges. It's a non-convex optimization problem. So the interesting question is, will this converge to the global solution? And as I said, there are zillions of papers on this. Depending on the row, you can put, if you say put a quadratic row, that's a sample covariance, that's the Gaussian case. So generalized Gaussian case, for example, if you put beta equals half, it's Laplace distribution. So T distribution, Tyler, Huber, Trim, lots of row functions, each with its advantages and disadvantages. And there are lots of authors, you probably know these names, these are famous people in signal processing and in statistics that all analyze these functions under different rows. Most of these work very nicely, but they are non-convex. I'm not going to talk about it in this talk, but one of the, I think, breakthroughs in the last 10 years ago was that we understood that when there is no structure in the problem, we can solve this problem even though they are non-convex. And if you're interested in it, this is because of something called geodesic convexity, and I can talk about it in the end if you want. What we still didn't understand is how to do it when there is structure. And that's what I'm going to talk about right now. So in many applications, estimating a covariance is hard. Think about it, if suppose you have a vector of size 100, then how many elements do you need to estimate? The covariance is 100 squared parameters, maybe half of it because of the symmetry. Okay, so you've got a lot of parameters to estimate. One of the tricks, very, very old tricks by Dempster and Lewitson, was what's called graphical models or Markov models, which basically assume that most of the elements are zeros. Okay, that's what's called the Markov chain. Mathematically, what does it mean? It says, we say that suppose we have 3 random variables, x1, x2, and x3. If we say that x1 is independent of x3 after we know the value of x2, which means conditioning on x2, then we say that this is a Markov chain. Okay, usually you talk about it in time. So you say the future is independent of the past given the present. Mathematically, it just means that the three-way joint distribution of x1, x2, and x3 can be decomposed very nicely into a product of 3 distribution, the marginal of x2, and then given x2, x1, and x3 can be independent, and they're just the multiplication of their scalar conditional distributions. That's in terms of probability. In terms of covariances, this means that because x1 is conditionally independent of x3, that in the 1-3 location and in the 3-1 index of the covariance, inverse covariance, you have a 0, which means you don't need to estimate it. You only need to estimate the points in the middle. So this is well known and it's very common all over. Conditional independence gives you sparse inverse covariance, allows you to estimate much less parameters, and gives you improved sample complexity. And people have been using it since, I guess, the 90s, something like that. For example, this is, I've been working a lot in Google about floods in India, forecasting floods. So this is an example actually from India. So here are rivers in India, and you see you've got the precipitation, the rain that we measure upstream, and we measure the discharge in the river in different locations. And given all this information here at the top, we want to forecast what's going to happen here. The important thing, how high is the water level going to be down here? The beauty of graphical models is that we can assume that things which are very far away are, let's say, the water level here and the water level here are conditionally independent once we know the height of the water here in the middle. And this gives us a kind of graph, you see, and we don't need to, every place there is an arrow between two, each node is a random variable. When there is an edge between two random variables, then we need to estimate their partial correlation. Otherwise, when there is no edge, it means we can just put a 0 in the inverse covariance. And then the inverse covariance has a very beautiful linear structure. We know which elements we need to estimate. And it can be, let's say, a matrix of size 1000 times 1000, but we only need to estimate 5,000 parameters instead of a million parameters, which would be the square. And that gives us a lot of computational and statistical advantage. The hard part of this problem is that nobody had no idea whether it's possible to solve such problems. So we've got this structure here with this objective here. Again, the question, will this solution converge to the global solution? Can it get stuck in a bad local minima, maybe even a saddle point? These are non-convex optimization. Our main result in this paper is that for almost all of these normal and reasonable rho functions, which satisfy some assumption, which all the interesting ones satisfy them, we can show you that any stationary point of the loss function is globally optimal, up to a multiplicative constant. That doesn't matter for the point of prediction. So this was a paper in Europe 2019 with Yoav and Afal. I think for me this was a very important result because people have been using graphical models with robust covariance estimation for a very long time now. And everyone knew their advantages, they knew it works well, but we didn't really understand why, because it's not convex. Here we proved for the first time that any stationary point is globally optimal. And the interesting question is, what did we need? Which assumptions did we need for that? So one assumption is on the top here, but that's not very interesting. That's very technical. The more interesting one is that usually, if you look at the maximum likelihood, you see we have here a sum, 1 over m, sum over I equals 1 to m. So we take a mean of IID samples. In our proof, we didn't take an empirical mean, we took an expectation. So it means you need to have lots of samples IID. So that's the important take-home message here, is that the problem becomes easy when you have many samples. So we already know, everybody knows, that when you have lots of IID samples, problems become easier statistically, meaning that you get better error rates. What we show now, that not only statistically, also in terms of optimization, the problem becomes easier when you get more samples, and if with few samples, you can get stuck in a bad local minima. But when you have lots of samples, everything, we say that the landscape becomes benign, and we can solve it exactly. Here are some examples. I think this is real data. I don't remember because it's from 2019. If this is data from the United States or India, I think it's India. We're trying to predict floods. These are the number of training samples. This is the normalized MSC of the river height. Let's start with the brownish curves. So here you see 3 curves. The difference between them are the robust functions. This is the Gaussian case, and these are 2 robust covariance estimators. This is with Laplace and this is with Tyler. You see that the robust versions give you better sample complexity. We get to better error. And this is not surprising because floods are very rare events. This data is very ugly and you've got lots of outliers. So it makes sense to use robust functions which are not sensitive to outliers and can handle a heavy tail distribution. So that's why these 2 are better than the Gaussian. Then what we have here, this orange, red, I don't know which color this is, it's kind of bluish color. These 3 are exactly the same, only with structure. What do I mean by with structure? These are with assuming also that there's a graphical model, which means that far away nodes in the river are conditionally independent given the rest. What you see here is that because of the structure, there are many zeros, we need to estimate many less parameters, and still you get better. This is the Gaussian case, and these are the robust cases. The robust versions are better than the Gaussian case and need many less samples. Here, for example, you need 100 samples for the same thing with a full covariance method. You need like 200 samples. Of course, after a while, the structure is not perfect. So you see, after 250 samples, it's starting to be better to use a full covariance matrix because you lose something of this because of the structure, which is suboptimal. So this is the first example. I think the take-home message here is that robust statistics are very important when you have outliers and heavy tails. Generally, usually they are very hard in terms of computation and optimization. In the unstructured case, we know that things become easy because of geodesic convexity. I didn't talk about that today. In the structured case, we showed you that if you have enough samples and if the model is correct, if you want, I can explain that later on, then the problem becomes easy. And maybe I'll get here, maybe I'll stop here for a few questions if you want about this part of the talk.
So we don't have any questions in the chat section, but if anyone has questions, they can unmute themselves and ask the questions.
Hello, sir.
Hi.
Sir, is this what we say G-convex functions? Are they similar to restricted convexity, which a general occurs in sparse estimation or that kind of this thing field?
Okay, I didn't talk about geodesic convexity. Geodesic convexity is basically when you do convexity, but not over a Euclidean space, but over a manifold. I think it is related to many other forms of convexity, but briefly, the whole idea is because these are positive definite matrices, then the line between them is not just like if you take a line between a point x1 and x2, then you say that alpha x1 plus 1 minus alpha x2. Here, what you need to do is you need to take a geodesic, which is the shortest path on the manifold. It's not in this talk, and that's for the unstructured case. What I talked here is the structured case, which is not geodesically convex. Maybe it is geodesically convex. The thing is that we don't know what is the manifold of structured positive definite matrices. So here we didn't prove convexity. We just proved that any global minima, any local minimum, any stationary point, which includes local minima, is globally optimal. Okay?
Okay, sir. Okay, sir.
Hello, sir.
Thank you.
Hello.
Yes.
Sir, but how can we validate that the local minima that we have got is the global optimal vector or the global optimal?
We prove it. This we prove. This is exactly what this. We prove that any stationary point is the globally optimal up to some multiplicative constant. That's the proof. Of course, it's under the assumptions that the true data comes from this distribution. In real data, we don't know.
Okay.
But if, for example, if the data is Laplacian and we solve the Laplacian-like robust likelihood, and we have enough samples, then I can theoretically prove that any stationary point will be globally optimal. Okay?
But in real data, we cannot say for sure because it may not follow any distribution, perfect distribution.
Definitely not. You are absolutely correct.
Okay. Thanks, sir.
The two things that make it easy here are exactly, as I said, this is what you asked about, that's the realizable model. Realizable means that we do with the model and the data come from the same distribution. If the true distribution is Laplacian, then we know the Laplacian likelihood. And the second thing is we need enough samples. We need lots of samples. And I think what this means is that you need a lot of samples and you need lots of models because you must use the correct model. If you use the wrong model, then you can have spurious local minima.
That in case of unbiased, biased data sets, like if one class samples are very less and other is abundant, so in that case, how to guess the distribution of the class with less samples?
You're absolutely correct. But if you don't have if you have unbalanced data sets, if you don't know the true realizable model, then these are very hard questions. And I think these are important things for future work. We didn't do that. But I think it's a really good question. Okay, so I think now maybe is a good time to continue. Let me go back to full screen. Okay, so that was the first question, the first example about robust covariance estimation. As I said, a hard problem in general, which is non-convex, but in some cases it becomes easy. When does it become easy? If you are in the correct model and if you have enough samples. Now let's talk about a different problem called principal component analysis. And I'm going to talk about the version of it that includes fairness. So let's remind everybody what is a principal component analysis, that's PCA. So we're trying to find the linear combination, we've got this data outside, trying to find the linear combination multiplied by this U, which is of norm 1, and trying to find the linear combination with maximal variance. That's the variance. If you take in the sum and you write the sample covariance as before, then we want to maximize this quadratic form subject to a unit constraint over U. And if you do that and you get all these points, then U gives you the error here with a maximal variance. And you see that this ellipsoid is mostly, it's a strong eigenvalue is in this direction. So U here will be the eigenvector associated with this direction here. Why is this important? It's important for importance because it tells you that this direction is more important than this direction. It's good for visualization. Suppose you have a vector of 100 dimensions and people still see only 2D or 3D. So you want to reduce the dimension to 2, 3 dimensions, and you want to look at the dimensions which are most important. And specifically, I came from a filter design because we're just trying to use our filters that we are going to apply to the data, and you want to apply catch most of the variance, maximum SNR, so it's exactly the same problem. That's why PCA and beamforming and all those filter design are very similar problems. PCA, I guess all of you know how to solve it. This is the most famous, I think, non-convex optimization, which everybody knows how to solve. Okay, you need to maximize this quadratic form subject to a quadratic constraint. It's non-convex because maximizing a quadratic convex function is hard. We want to maximize concave function, and this is convex. Yet everybody knows how to solve this. You just take the Lagrangian, you put a dual variable lambda on the constraint, you take the derivative with respect to U, and you see that U must be an eigenvector of S, and the lambda, the eigenvector value, gives you the objective. So we know that U is an eigenvector of S, associated with the eigenvalue lambda. The global maximizers here are plus minus Umax, where Umax is the eigenvector associated with the maximal eigenvalue. The global minimizers are plus minus Umean, where Umean is the eigenvector associated with the minimal eigenvalue. And in between, you've got lots of saddle points, but all of them are good. What do I mean good? People today call it strict saddle points or rideable saddle points. The main idea is these are saddle points that you don't get stuck in. You just, if there's a little bit of noise, there's always a strong descent direction where you can go. And therefore, if you do gradient descent on PCA, you will easily find the minimizer. If you do gradient ascent and climb up the hill, then you find Umax, which is PCA. So this is a non-convex problem with saddle points, yet everyone knows how to solve it, and nobody is afraid of working with it. In fact, one of the ways to work with it, to prove that it is so easy, is what's called semi-definite relaxation. The main idea here, this problem is indeed non-convex because you have here the u times u. So you just invent a new variable called p, which is u times u. And now every place you have u and u, you write p. Then this problem here and the problem on the top are exactly the same. The only difference here is that this was quadratic in u, and this is linear in p. So this is convex, this is not convex, this is easy, this is hard. But these two problems are exactly the same, so how can it be that this one is easy? The difference is that you have this rank here, constraint, that you need to keep it. And what we do in the semi-definite relaxation, we throw away this non-convex rank constraint. And people know today you can prove that even if you throw away the rank constraint and don't constrain P to be rank 1, you still get an optimal solution, which is rank 1. And this is also known to be the Lagrange bidual, and it's a convex optimization, and people use it all the time in beamforming in the old papers. Let me now show you another approach of seeing PCA. Is today, I think many of you probably don't think about it as trying to maximize the variance, but trying to do dimensionality reduction. What do I mean? You take an xi, you want to reduce it to some code here of lower dimension, and then be able from h to go back to x without losing any information. And this way you kind of compress it. So you take x, you multiply it by v transpose x, that's in low dimension, then you multiply it by u to get xi again. And you want to find u and v, which will not lose information, but here in the middle, you want to have something which is very low dimensional. Specifically in PCA, we know that v can just be u exactly, and we get this optimization. And if we do semi-definite relaxation, it just means that instead of writing u transpose here, which is non-convex because it's quadratic and then quadratic again, we write u times u transpose is p, and now this is a linear inside quadratic, which makes it convex, and this constraint here, which is not convex, you replace by semi-definite constraints. So people have been doing that a lot of times, and this too works very nicely. Why am I talking about it? Because now, for example, you can do something that you couldn't do before. Remember at the beginning I talked about robust covariance estimation? Suppose you have outliers and you want to do robust PCA, then you don't want the 2 here, you don't want to take the square. Remember that's what I said at the beginning, you prefer, let's say, absolute value over a square to ignore outliers. And now it's very easy to do it because it's still convex. And this is robust against the outliers. Instead of L2, we work with L1. You think about it, it's like if this was a scalar problem, then L2 would give you the mean, L1 gives you the median. And so this is robust PCA. and it works only because of semi-definite relaxation. And now let me ask you a question. So L2 is regular PCA, L1 is robust PCA. What would be the opposite of a robust PCA? Now I'm checking if you are awake. Let me ask again. L2 is the standard PCA. You just put a 2 here and you get PCA, which is very nice, everyone knows. If you have outliers, then you remove the 2 here, you get an L1, and that's good for rejecting outliers. What is the opposite of rejecting outliers, of being robust?
So probably we can use L21 norm.
Yeah, so L2 is the regular one.
L21,
L2 is
L21,
regular.
L21 norm, L21 norm.
Yeah, but that's okay. That would be something in between. But I want the complete opposite. L2 is the standard, L1 is one side. That's the robust case. What would be the other side, the other extreme?
Probably L0 norm.
L infinity.
L infinity. What is L infinity? What will that do?
Max norm, that will just take the maximum. Mainly it will consider the outlier itself.
Exactly. And when will that be good? Why would you want to do that? When will you want to consider the outlier?
Probably we'll check where the outliers are and we can remove them using that.
Anomaly detection.
No, let's think about an idea, a problem where the outliers are the good thing, are important. That's very common today in machine learning. Anomaly, no. Anomaly is again a bad thing. When don't we want? Think about it. When you say outlier, you mean that there is something in the data set that you want to throw away. Today, in machine learning, we don't want to throw away people because that would not be fair, right?
Thread detection.
Okay, so let me continue. So the opposite, as you said, of robustness is what's called fair PCA. Fair PCA is when you don't want to throw away everyone, but you want to treat everyone equally. Okay, you want to be completely fair towards everyone. And then instead of using L2, you go to L infinity. This promise that you will be fair, that you will treat everyone equally. It's a problem for filter design. People have been working on it in beamforming for many years already. You see, here's a paper, I think more than 10 years ago. Think of a system where you have 5 users and in communication, and one user is far away. You don't want that user will not be able to receive everything. You want to treat everyone equally. Specifically today, this is a work from 2020, I think, in Europe, fair PCA. Think about a data set where you have females and males, or maybe Indians and Israelis, and you have the different groups, okay? And all of the groups are important. No one is an outlier, but some group, as someone asked before, the groups may be unbalanced. Maybe you have only 10 samples from one group and 100 samples from another group. You want to treat everyone equally, right? If you would do a robust PCA, then robust PCA will just think that the small group is an outlier and will throw it away, okay? Fairness is exactly the opposite. Let's treat everyone equally. So that was a paper last year in Europe. Again, exactly as before, only instead of having a sum here, we have a minimum because we treat the worst case. As before, this was non-convex. They said, let's use the same trick, U times U transpose, call it P, semi-definite relaxation, and this is the problem they suggested. This is not tight, which means it doesn't always succeed, but they gave a proof that it is neo-optimal when the rank is much larger than the square root of the number of groups. And they gave an algorithm how to, from P, how to find U in a randomized manner. So this work was concurrent with our work, and but then we did something completely different. We said we didn't want to do a SDP. We wanted to try to do it using regular gradient descent. Their work is really amazing here because it gives you this proof here, which I think is really remarkable. But the hard part is you need to solve an SDP. We said, can you just do gradient descent? So we said, let's try to find U, which will minimize the squared loss over the worst group. Specifically, we didn't talk about groups. We said that every sample is a group on its own. So we tried to solve the unconstrained mean squared error formulation using SGD. We noticed that it usually works very nicely, but that it's non-convex, and that it's a bit better if we use their SDP initialization. The nice part, I think, in our work is that we said we already know the papers in beamforming showing that this paper is generally non-convex, and we can show that it's NP-hard. What we showed is that we found conditions when it's very easy to solve it. Specifically, we showed that when the groups are orthogonal, are completely orthogonal, then the problem becomes very easy. What do I mean orthogonal? Suppose the vectors xi and xj are orthogonal for every pair. Think, for example, suppose you're allowed to have only 3 vectors, but you want to be correlated with all the d dimension n equals 4 unit vectors. Okay? To completely catch all the 4-dimensional unit vectors, you need 4 vectors, but you are only allowed 3. How do you choose which 3? You want them to be somewhere in exactly the middle. And what we show is that the optimal correlation is the rank divided by n. Semi-definite relaxation, which is the trick I showed you before, is tight, which means it gives you the right solution. It gives you the optimal correlation, but it does not find the vectors because it gives you a solution which is not feasible. But on the other hand, we prove that if gradient descent, every local minima is globally optimal. So you can just do gradient descent and it will work. Let me show you some examples. So here is a SDP relaxation, and these two are gradient descent. The green is regular gradient descent with random initialization. The orange is you start off with SDP and then do gradient descent. And you see that already at ranks, which are like 2 or 3, we're already close to optimal. We also checked the quality of the approximation as a function of the orthogonality. And as soon as you are even a bit orthogonal, you see that gradient descent finds the optimal solution immediately, even though SDP doesn't. Here is also on some in beamforming applications with hyperspectral data. And here is even the paper I showed you of the SDP. This is their example, and their algorithm is what you see here, the red. For some reason, which I don't really understand, and it's a matter of luck, sometimes it does succeed, but in their example, the SDP gets it wrong here, whereas gradient descent succeeds. Gradient descent is the green one. So I think it's a fluke. I mean, I think the SDP is amazing. I think that if you have the computational power, then you should first do SDP and then do gradient descent. But there are conditions, especially when the data is orthogonal, that gradient descent just works amazing. Take-home message. PCA is probably the most famous and most important non-convex problem, which is easy. Everybody knows it's non-convex, and everybody knows that all the algorithms solve it very easily. It's hard to fail in solving PCA. But as soon as you tweak it a bit, it becomes very hard. If you want to tweak it to the robust case, then you change L2 to L1, then there are papers on it. We took the other direction. Instead of being robust, we wanted to be fair, which is exactly the opposite. And then it's known that it's NP-hard, but we showed that it is easy when the vectors are orthogonal. And I think it's a good time for questions.
So, yeah, go ahead. Yes,
Yeah.
yes.
Sir, how do we choose the rank?
How do we what?
Choose the rank which was chosen to be equal to 2 in your presentation, in your simulation results?
It's a very good question. In general, when we do a gradient descent here, we need to choose the rank, because as you see here, we put this U here, so we need to decide on the rank beforehand. What we usually do is we start with a larger rank than what we need, see if we succeed, and then reduce it. In the SDP formulation, you don't need to decide on the rank beforehand, but you need to, usually you need to play with the trace here a bit. Sometimes you need to play with the 1 year. Because this trace here, it's a surrogate function for the rank. But it's a very good question, and we don't have an answer for it. There are many works on it, not in fair PCA, but in general PCA, how to find the rank.
But sir,
solving it for fair PCA, I think, is a good open question.
But so wouldn't it be better if we have the higher rank matrices than to have a lower rank matrices, because rank 2 will be a rank deficient matrix. So wouldn't that be a problem in solving the PCA?
You're saying, again, repeat the question?
Like rank 2 will be a rank deficient matrix, no? So would it be better to have a rank deficient matrix to solve the like maximum or the minimum value of the optimization problem, because rank deficiency usually causes the singularity issues.
You are right, but that's the whole point here. The whole point here is to find the low dimension. If I don't put the rank constraint, then it will be easy, but then I will not have dimensionality reduction. What happens here in the SDP, it's somehow similar to what you're saying, because the P generally can be full rank, and you just constrain its trace. But the idea here is that hopefully the trace will make it rank deficient.
But then wouldn't it be better to have then the complete rank deficient that rank equals to 1 itself, not 2 or 3, something like that?
The hope is that if the true data is, let's say, of rank 3, then we will be able to understand that it is rank 3. That's what we hope. If the data is of higher rank, then we want to understand it.
Okay, sir. Okay.
Sir, one more question at this point.
Yeah.
Sir, are we restricting that rank should be exactly equal to, say, what we are specifying? Means, say we specify that rank equal to 3 matrices we are looking for. So will that procedure means, is our constraint like that, or is our constraint like rank of the matrix is less equal 3?
So specifically, I'll talk about our algorithm. Here it depends on the SDP and the rank reduction algorithm, but in our problem, we say that we fix the U. By fixing the size of it, it's an upper bound on the rank. Right? Suppose this is a matrix which is 100 over 5. then the rank cannot be larger than 5, but it can be smaller. Usually it will try to find the largest it can, because it's easier for it. So the algorithm will converge to something which fills the whole matrix. But theoretically, we're not constraining it to be exactly equal. Okay?
Sir, means by allowing rank equal to be say 5, actually we can solve the problem when rank is equal to 2, say, suppose.
Yes.
Okay, sir.
Yes, but I do not think it will. I think that what will happen if you allow it rank 5, then it will find something of rank 5. It will, even though reality is rank 2. But you are right.
Okay, sir.
It also probably depends on which algorithm you use for descent.
So probably we'll have to go for the greedy solutions and have to check every time if what value of the rank is working correctly for my problem.
Exactly.
Okay, sir. Okay, you can go ahead, sir.
I think we're out of time. Do you want me to talk for 5 minutes quickly on the last problem, or do you want to finish?
Oh, so you can wrap it up in 5 minutes.
Okay. So let me just quickly mention what is the problem without the details. So the last problem is again a problem which is interesting both in signal processing and in machine learning, which is binary regression. Again, it will be a problem which is generally NP-hard, but we will show conditions when it is easy. So let's start with the communication formulation or the signal processing. Suppose we have data, which is X is some kind of channel, W are bits, okay, plus minus 1 bits, BPSK if you know communication, V is noise. We measure this Y, and somebody is sending us in communication these W's, and we know Y and we know X, and we want to detect what W was, what were the bits. We used to call it multi-user decoding or MIMO decoding. Lots of works on this. Today, in machine learning, people do exactly the same thing for a completely different reason. Think of this as some kind of neural network. It can be a linear regression, it can be robust regression, it can be logistic, it can be cross-entropy, it can be deep learning, some kind of F, okay? And you want the weights to be binary. Wi squared means that Wi is plus 1 or minus 1. Why would anyone want to have a binary weights? These are not bits, this is not communication. They want to do it because it's good for storage. Deep neural networks take a lot of storage and power consumption. If we just work with bits, it's going to be much cheaper. So there are lots of works on doing binary regressions, binary deep learning. Let me skip this. Okay, no. The standard approach in deep learning today is something called straight-through estimator. The idea is, because they want a W to be binary, they say, okay, let's say W overlay is not binary, and take its sign. The problem is that the sign is non-differentiable, and that's why we ignore the sign in the backward part of the backprop algorithm. And this works amazing. But we tried it in MIMO detection and stuff like that, and then it completely fails. On the other hand, in linear regression, MIMO detection, we know that there is an old history of what you should do. What we usually do is SDP relaxation or Lagrange relaxation, which says we have a constraint here. Let's write the Lagrangian, add a dual variable Zi for each of the constraints. But now instead of having only a minimum optimization, now we have a saddle point, max and the mean. And you can think of it of trying to, you do one step in the W, one step in the Z. It's very common today, people do it in generative adversarial networks all the time. So we said, let's try to do it. Let's skip here. Okay. And the question is, can we do gradient descent and solve this problem? So you see, this is a gradient descent. In the W direction, this is a gradient ascent because we want to climb. We want to find the maximum in the Z. Saddle points are something which is not very well understood even today. It's not even clear what exactly is a local saddle point, but I will jump over this. And today there are conditions for something called the local maximum. And what we wanted to check is whether there can be bad local maximins or all the local maximins are globally optimal. And what we proved in this work is that if there is very small noise under this model in the Gaussian case, but very small noise, the highest amount, then we know that semi-definite relaxation solves this problem. And we show that the every local minimax point is also globally optimal. That was in the linear regression case. We also showed it in robust regression case. So even if the function is, let's say, Huber, which we showed at the beginning, but we have very few outliers, which are very large, then we can also solve it. And let me show you some results. So for example, here, you see error probability as a function of the noise variance. So SDR, that's a semi-definite relaxation. That's just like the maximin L2, but maximin L1, there is no semi-definite relaxation for L1, gives you much better error probabilities. And you can also see it in real data sets. When you have outliers, maximin L2 here gives you much better errors on real data sets because you take into account the outliers and you don't get stuck in bad local minimas. It's not local minimas, it's local saddle points. Here are the weights in MNIS. And I think that I just wanted to show you. If you're interested, you can read the paper. It's an archive. And to conclude, I showed you 3 examples of optimizations which are very interesting, both in signal processing and in machine learning. All 3 of them are non-convex and usually NP-hard. But I tried to show you that under some conditions, they become easy. And I think it's important today to understand when can we solve such optimizations. The things we showed are realizable, which means that the true data comes from the model we assumed. Population, which means that we have lots of samples. Low noise makes things obviously easy. We knew that it makes everything easy in terms of statistics. Apparently, it makes things easy also in terms of optimization. In PCA, when things are orthogonal, which is in some sense the hardest case, because it's harder to reduce them to the same subspace, things become easy. We also discussed robustness, that it's the opposite of fairness. And I think it's important to understand when and why things work. Thank you for listening, and I'm open for questions.
Hello, sir.
Yes.
Sir, can you go to last work, sir, where weighted, sir, there came an eigenvalue of a weighted matrix, X transpose some diagonal matrix times X, something of that form. Yes, sir, this yes, right? Sir, what happens if D diagonal of D is, this quantity is very, very small?
Then it will not work.
Hello, sir?
It will not work. Usually it will. Okay, I'll be very frank. This last work, min-max, the first 2 we understand very well because these are minimization problems. Minimization problem is something that we work, I think everyone today for the last 50 years, we understand them very well. Min-max optimizations are much, much harder. I'm guessing all of you tried to run deep learning with generative adversarial networks, and you know that it's very unstable. These things don't work well. It's very, very hard to succeed in min-max optimizations. Usually, it's not that it sometimes doesn't work. It usually doesn't work. You need to really have large dimensions and very few outliers, which are very big. The only thing I can say is that there is more that we don't understand about min-max than we do understand. And if there is this is the problem which I think is most interesting these days, and I suggest that I recommend many of you try to solve it, because we really don't know what's going on there. It's a great topic to work on.
Sir, one more question at this point. Sir, recently one work came up, globally convergent iterative reweighted least squares. Is this, sir, this in this framework, will that IRLS approach work?
So I think this is very similar to the works here. I think there are lots of works, as you just said. Like here, at the beginning. No, wait, I got lost. Here, like this paper is amazing on doing IRLS like approaches for non-convex landscapes. There's a work by Montanari. I don't think he uses IRLS, but we do know that the landscape of robust optimization is sometimes benign. And these are works which I really like. And I think it's related. And you are right that the standard approach to solving this thing is using IRLS. That's how we use it too.
Thank you, sir.
Sure.
Any more
I'm
questions?
sorry I can't be with you there. I wish I could see you face to face.
Yeah, you can switch on your cameras. All the students can switch on the cameras, and we can have a group photo for probably at the end. Any questions? Okay, I think.
Thank you again for the invitation, and I hope everybody will be healthy.
Thank you, sir.
We'll
Thank
see
you.
in conferences.
Thank you very much for accepting our request. And I am sure that all the students will be getting benefited from this talk, and they will definitely use this in their research work. I would like to thank all the students for joining. And finally, I would like to thank Professor Ami Wiesel for accepting our request and delivered such a beautiful and amazing talk. Thank you, sir. Thank you very much.
Thank you.
Have a nice day, sir. Thank you.
Bye-bye. Feel well.